Somewhere in the universe, there is a shortcut. Everything you know about distance is about to be wrong. Wormholes are real, at least on paper, and that's the problem. Imagine folding a piece of paper. On one end, Earth. On the other end, a star 1,000 light years away. Normally, traveling between them would take longer than human civilization has existed. But fold the paper, bring both ends together, and suddenly, the distance between them isn't 1,000 light years. It's the thickness of the paper. That's a wormhole. And here's what nobody tells you. The mathematics that proved Einstein right about black holes, gravitational waves, and the expansion of the universe. That exact same mathematics also says wormholes can exist. We just have never found one. In 1935, Einstein and his colleague Nathan Rosen were studying the equations of general relativity, the same theory that predicted black holes decades before we confirmed them. And buried inside those equations, they found something unexpected. A black hole, mathematically speaking, doesn't just have one end, it has two. An entrance and an exit, connected by a tunnel through the fabric of space-time itself. A shortcut between 2 points in the universe that could be impossibly far apart in normal space. They called it an Einstein-Rosen Bridge. We call it a wormhole. The mathematics was real, the equations worked, the geometry of space-time genuinely allowed for it. The problem was everything else. Here's where the theory runs into reality. The wormholes that Einstein's equations describe are not stable. The moment anything, even a single photon of light, tries to pass through one, it collapses. Instantly, the tunnel closes before anything can cross it. And even if you could somehow keep it open, the conditions required to create one in the first place involve densities of matter and energy that make the core of a neutron star look gentle. But in 1988, physicist Kip Thorne, who later won the Nobel Prize in Physics, asked a different question. Not whether wormholes exist naturally, but whether a sufficiently advanced civilization could theoretically construct and maintain one. His answer, buried in peer-reviewed mathematics, was yes. Under one condition: exotic matter. Not exotic as in rare, exotic as in matter with negative energy density. Matter that pushes outward instead of pulling inward. Matter that could hold the throat of a wormhole open against the forces trying to collapse it. Here's the disturbing part. Exotic matter isn't just theoretical. We have already observed something that behaves like it. The Casimir Effect, a real measured, reproducible phenomenon, demonstrates that between two closely spaced metal plates in a vacuum, the energy density drops below zero. Negative energy, measurable in a laboratory right now. It exists, just not in quantities anywhere near large enough to hold open a wormhole, yet. But here's where wormholes stop being just a transportation problem and become something far stranger. If wormholes connect 2 points in space, they may also connect 2 points in time. General Relativity treats space and time as a single unified fabric. Space-time. A wormhole that shortcuts across space could, under the right conditions, also shortcut across time. One end of the wormhole could exist at a different point in time than the other, meaning, in theory, a wormhole isn't just a faster way to travel between stars. It could be a door into the past. Kip Thorne's own calculations showed this, and it created what physicists call the grandfather paradox. If you travel back in time and prevent your own existence, how are you there to do it? The logical contradiction seems to make time travel impossible, even if the physics allows it. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel from ever being possible, even when the equations seem to allow it. That every time a wormhole gets close to becoming a time machine, quantum effects destroy it before it can function. Nature, Hawking suggested, protects its own timeline. We don't know if he was right. Here's where we stand today. Wormholes are mathematically real. They emerge naturally from the same equations that have been proven right about everything else. They require exotic matter to stay open, and exotic matter has been observed at small scales. They may connect not just distant places, but distant moments in time, and we have absolutely no idea if any exist naturally in the universe right now. We have never detected one. We have never observed any signal that suggests one is nearby. We don't have the technology to create one, and we don't fully understand what would happen to anything that passed through, but we haven't ruled them out either. The universe has surprised us before. Black holes were mathematics before they were reality. Gravitational waves were equations before they shook our detectors. The expansion of the universe was a theoretical curiosity before it became the defining fact of cosmology. Every time we said the universe couldn't do something, the universe did it anyway. Wormholes may be the next thing we were wrong about. And somewhere in the fabric of space-time, in the geometry of a universe far larger than anything we can observe, there may already be tunnels connecting places and times we can barely imagine. If wormholes can connect 2 points in time, what would you change if you could go back? Follow Hidden Cosmos, because the next video answers something even harder.